Sir, hello? Hello?
Hello, sir. Sir,
Can you hear
before we
me?
start, yes, sir, you're audible.
But where is my photo?
I think your photo is still visible there. You don't have to.
Do you see me?
Yes, sir, we can see you.
But I can't see myself. Something. ये क्या है?
नहीं, can so that's
yeah,
you.
Then. Oh,
Okay, so that's that. But I think no, I think the organizer has control on this one. So you don't really put yourself. No?
Upel, can you show my
Passwords, controls.
yeah?
Don't worry about that. Just go and start talking.
Okay. All right. Do you see me?
Yes, sir.
Okay. I'll start then.
Sir, yes, sir. Before we start, I'd just like to give a brief introduction.
Okay.
Yeah. So, hello and welcome all quantum computing enthusiasts to this talk by Professor Anil Kumar on quantum information and processing by nuclear magnetic resonance. Sir is an experimental physicist and a professor at IISc Bangalore, widely known for his work on NMR spectroscopy and quantum information processing. A graduate of Meerut College, Agra University, and an alumnus of IIT Kanpur, he has collaborated with Nobel laureates like Robert Ernst and Kurt Wuthrich. I'd like to hand it over to Sir now to enlighten us on this beautiful topic.
Okay. Welcome to this presentation. The title of my talk is Quantum Computing and Quantum Information Processing by NMR, Why and How. So basically it is going to be an introduction, and I will only in the later part show some couple of experiments which you will perhaps enjoy. Okay, let me tell you the NMR phenomena. The interaction energy between a magnet and a magnetic field is given by this equation, and for nuclei, mu is equal to gamma h cross I. And so if we have a B naught field in the z direction, then the interaction energy becomes proportional to Iz and B naught, and gamma depending on the nucleus that you are looking at. So the degeneracy of these two levels gets lifted in a magnetic field. The difference between this energy is gamma h cross B naught is equal to h cross omega naught. Omega naught is called the Raman frequency. Its resonance condition is given by this. This most commonly used nucleus is the nucleus of hydrogen. Its resonance Raman frequency in a magnetic field 2.35 Tesla, which is equal to 23.5 kilogauss, is 100 megahertz. Other spin half nuclei are F19, which is in the same magnetic field, has a resonance frequency of 94 megahertz, and carbon 13, which is a 1.1% natural abundance, has a resonance frequency of 25 megahertz. The NMR was first detected by Bloch from Stanford and Purcell at Harvard in 1945, for which they shared the 1952 Physics Nobel Prize. Now, NMR has two major and one minor applications. The major applications are structures of biomolecules in solution, and now MRI, which has now become a household name, and also a minor application is quantum computing. I have participated in all the three activities of NMR, and I will briefly mention those. So, for example, for doing structures of biomolecules in solution, we used this experiment that I did in 1979-80 when I had gone for 1 year to Zurich. It's called nuclear overall effect spectroscopy. What it is showing is that this is a two-dimensional spectrum, omega 1 and omega 2. Along the diagonal lies the normal one-dimensional spectrum of the protein, and each cross peak here is an indicator of the distance between this proton and this proton on the diagonal. And so it has this experiment has almost complete information about the three-dimensional structure of a protein. Uh, this also has more than 2,000 citations. I expanded BVRC here. It's a Biophysics, Biochemistry Research Journal, Communication. Professor Wittrich, Kurt Wittrich, sorry, Professor Richard Ernst got the Chemistry Nobel in 1991 for development of one and use of one and two-dimensional Fourier transform, NMR. Kurt Wittrich got the Chemistry Nobel in 2002. Actually, it was expected that these two people would share the Nobel Prize in 1991, but that did not happen. Wittrich had to wait for another 11 years to get his Nobel Prize for protein structure determination in solution by NMR. So, if I go back, Ernst got the prize for development of techniques, and Wittrich got the Nobel Prize by using those techniques, getting the structures of proteins in solution by NMR. Second major application of NMR is MRI. Everybody knows this word, magnetic resonance imaging. I had done an initial experiment way back in 1975, two tubes of water using what's called a NMR, two-dimensional MRI, Fourier 2D MRI experiment using gradient in x direction and z direction. And therefore, when the two-dimensional spectrum is displayed, it identifies these two tubes of water which are displaced. This was the first Fourier imaging experiment of MRI. Oops. Why is not going? Ankur, you have to come. It's not moving. Hello? 1 minute. Ankur, come. Slow, it doesn't move. What is it? My putty. What did you do? Click. Eh? Click. Wait, huh? So the image quality improved. This was not my work. This was the work of hundreds of people who developed the MRI. And by 1990, it was clear that MRI is going to be extremely useful. And so now the MRI is a household name, and it actually looks at the protein distribution, and it's a T1 T2 dependence, gets T1 T2 contrast, and you can focus on any part of the body, like a knee here, lumbar here, liver, brain. Brain is a major application, and so on. The initial experiment of 1D NMR by Paul Lauterbur was the first two tubes of water he had imaged first. And so the Nobel Prize for Physiology and Medicine for discovering the MRI went to Paul Lauterbur and Peter Mansfield in 2003. MRI has revolutionized human radiology, and it is hailed as a major contribution of 20th century science to humanity. Now come to the topic of the lecture, which is quantum computing and by NMR. Okay, this is now the starts introduction to the quantum computing by NMR. All present-day computers, we call them classical computers, use binary logic, 0 and 1, and all computation follow from this yes and no answer. Feynman in 1982 suggested that it might be possible to simulate the evolution of quantum systems efficiently using a quantum simulator. He never talked about computing, he talked about simulation only. But it was a good enough suggestion because it immediately triggered a lot of activity in all fields which possibly could build a quantum computer. But then what is so special about quantum systems that is not there in classical systems? So there are two important properties. One is called coherent superposition. The coherent superposition means this: if a classical bit can exist either as 0 or 1, but a quantum bit, we call it qubit, can exist simultaneously in 0 and 1. It's coherent superposition idea, and this gives rise to tremendous new possibilities. It gives the power to the quantum computer because of this possibility of coherent superposition. The other important property of quantum system is entanglement. For example, if you take the EPR states, 0, 0 plus 1, 1, it is not resolvable into tensor products of individual particle states, and such states are therefore called entangled. This entanglement property gives rise to quantum computing and teleportation, etc. Of course, to make use of the quantum properties of a qubit, one has to write algorithms which utilize the properties of either coherent superposition or entanglement, or both. For example, one of the very important application which is still being searched is called prime factorization. Classically, the prime factorization complexity increases exponentially as the number of digits go up. The point is, you want to find out what are the factors of a big number, and this, if you use a classical computer, will take age of universe to factorize such a big number. Now, our bank accounts are safe, military communications are safe because you cannot really find the factors using a classical computer. However, Shor gave a quantum algorithm in 1994 and showed that the complexity increases only logarithmically as the number of size of the digit increases. And so, if we had a quantum computer with the same speed as the classical computer, it could factorize a 400-digit number in 3 years. This information was revolutionary, and everybody wanted to have a quantum computer because, especially U.S. military, they spend a lot of money in trying to develop this, and they want to be the first one to get a quantum computer. Of course, the building of quantum computer took off very, very slowly. It is still going on, but still not reached anywhere. I will show you a slide in the later part of the lecture. What is the status? There is searching an unsorted database. For example, if you have a telephone directory and you want to know what is the name of a particular telephone number, you basically have to go through the whole directory. On the average, you need 9x2 operations. But Grover, a graduate of your institute, IIT Delhi, he was working in Bell Labs, and in 1997 gave a search algorithm using coherent superposition. And you need then only root n operations. This is very significant. This is just for demonstrating the power of the quantum computer. There are certain class of functions which are either constant or balanced. Classically, it takes several steps to distinguish the constant and balanced functions. But Joshua, it's called the DJ algorithm in 1992, demonstrated that it can be done in single step. quantum algorithm for linear system of equations was demonstrated by Seth Lloyd and his colleagues, and they showed that the quantum computer gives the exponential speed up. There are many experimental techniques which are being explored for quantum computation, and we have not yet come to the last of those techniques, but the many of them, trapped ion, two people got a 2002 Nobel Prize for this trapped ions, polarized photons, lasers are very active. Right now, quantum communication has been set up through satellite by China and by India also. Gravity quantum electrodynamics is not taken off too much. Then quantum dots is also going on slowly. Uh, Cold atoms and very difficult, and NMR. But the maximum progress has been done by Josephson junction qubits. It's called superconducting quantum computer. And I will, in the last part of my talk, show you some use of this technique of Josephson junction qubit system. All right, we come back to NMR. Okay, we are NMR technicians. We work in development of NMR techniques, and so we also explore quantum computing using NMR, why and how. Okay, your nuclear spin has a small magnetic moment and behave like tiny quantum magnets. When placed in the magnetic field, they either orient parallel or anti-parallel to the magnetic field if they spin half nucleus. A transverse radio frequency field B1, which tuned to the lambda frequency spins, can cause transitions from 0 to 1. It's a NOT gate by a 180-degree pulse. So we apply a 180-degree pulse, which we routinely do, but it's a NOT gate. We have never realized that we are doing a NOT gate when we are applying the 180-degree pulse for the last 50 years. Or put them in coherent superposition using Hadamard gate by a 90-degree pulse. And we also do 90-degree pulse all the time in NMR experiments, be it chemistry, be it biology, but we never talked about as a Hadamard gate. So these are single qubit gates, NOT gate, Hadamard gate. Spins are coupled to each other by what's called indirect spin coupling, and this was also discovered soon after the discovery of NMR, and is used heavily in looking at the structures of organic molecules and now biomolecules. So it's very indirect spin coupling between spins on the same molecule is a very great source of information. But here, this indirect spin coupling are used by quantum computing methods, and we can do, for example, a control NOT gate using J coupling. So multi-qubit gates. So the sum total of this transparency is that nuclear spins are qubits. We need a very good magnet, which is not only just high magnetic field. For example, this 500 megahertz proton frequency of 500 megahertz, 11.5 Tesla. But it also has to have a very good homogeneity and stability. Is 1 ppb, 1 part per billion. So we should be able to, in a 500 megahertz spectrometer, have a line width of 0.5 hertz. This was developed for getting structures of organic molecules and biomolecules. So this whole thing has been used mainly for structures of organic molecules and biomolecules. But we just use this same hardware. We have an NMR research center here, is one of the best centers in India, has 7-8 spectrometers, and each of these have a homogeneity and stability of 1 part per billion. These are, of course, commercial magnets. Many of these are from Booker. This is 700 megahertz. We have now 800 also. We have not yet got a 900 or 1000 megahertz. Many people have got 1000 megahertz in USA. All right, let's. Question is, why NMR? A major requirement of quantum computer is there any question right now? Hello?
No,
Hello?
sir.
Is there any? I pause for a minute.
Yes, sir. I think we're all clear on this till now.
Okay, fine. So the question is why NMR? Uh, I mean, I'm a salesman of NMR, so I'm trying to sell you NMR. A major requirement of quantum computer is that the coherence should last long. Coherence means when you put these things in coherent superposition, that coherent superposition should last long. It so happens that the nuclear spins have a very tiny magnetic moment and it interacts very weakly with the environment. So it retains its coherence for very large time, of the order of hundreds of milliseconds, and the longitudinal state for several seconds. This is the main reason why we are uh, uh, trying to say that we can use NMR for quantum computing. Okay, and you can transfer information from one qubit to another qubit through the coupling network, coupled spins. And unitary transform can be applied using radio frequency pulses and J evolution. I will show you this. And various logical operations and quantum algorithms can be implemented. Okay. The, the, the problem in NMR is addressability problem in NMR. For example, an NMR sample tube, which is about 0.5 ml of liquid, uh, and we do it always in the liquid state right now, okay, has something like 10 to the 18 spins. So the question is, do we have 10 to the 18 qubits? Sorry, we don't have 10 to the 18 qubits, but we cannot individually address them. Maybe in future we can do a MRI type of experiment and we can individually address them, but it's far-fetched. So the progress so far that we have done, whatever we have done so far, spins having different Lama frequencies can be addressed in the frequency domain, resulting in as many qubits as Lama frequencies, each having 10 to the 18 spins. So what we do is we are doing ensemble computing. So if suppose we have, I will show you the molecules, which how they form qubits. Okay. So, but then we have a large number of identical molecules giving rise to a signal of one qubit, each qubit. One needs unequal couplings between the spins, yielding residual transitions in a multiplet in order to encode information as qubit. Okay, here is a very good molecule. It was synthesized in our lab through the known synthesis. It's a carbon-13 enriched fluorine proton system with dibromo. Okay, bromine is not used. It decouples itself with the rest of the spins. And we have a 3-qubit system, heteronuclear 3 spins, fluorine, carbon-13, and proton. In a 500 megahertz of proton resonance, the proton spectrum looks like this. On the carbon-13, it resonates at 125 megahertz, and in fluorine, it resonates at 470 megahertz. So we need three RF sources: 500 megahertz, 125 megahertz, and 470 megahertz. We have those in those spectrometers. The couplings are very important. The single bond couplings are large, and 2 bond couplings are 50 hertz or so. Okay. But homonuclear spin, that means proton-proton systems having different chemical shifts, also form multi-qubit systems, such as suppose you take chloroform, unlabeled chloroform. So you have a single proton, it's a 1-qubit system, single line. Okay, you just take a chloroform, put it in the NMR sample tube, you get one proton signal at Lambda frequency of the proton. If you have this molecule, the neighborhood of this proton and this proton are not identical. So they have what's called chemical shift. Therefore, they resonate in about 100 hertz away from each other, only 100 hertz, but we have a magnetic homogeneity of 0.5 hertz, and they have a coupling of about 5 hertz. So we need very high homogeneity so that the line width is not very large. So this is from 2-qubit system. There are 3 protons in this molecule, and there are 4 energy levels here. There are 8 energy levels here. We can call them 000, 010, 001, and so this is single spin flip. These are 2 spin flips and 3 spin flips states. In fact, for me, we used to call them alpha, 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 beta, alpha, alpha beta. For me the largest difficulty was change my notation from alpha to 000 or 010, and once I overcame that barrier, it was everything was clear. Okay, so this is how we form qubit systems. But story is not over. We need pure states, which means if you look at the density matrix of the system, then the trace rho and trace rho square should be 1. For a diagonal density matrix, this condition requires that all energy levels except one have zero populations. Such a state is difficult to create in NMR. And David Corey from MIT came up with a clever idea saying we will not have pure states, we will create pseudo-pure states. What he meant was he will expand the density matrix in high temperature approximation, which is a very good approximation, and therefore your alpha is about 10 to the power 5 and 1 this is delta rho. So we create a state in which all levels except one have equal population. Such a state mimics a pure state. And so, for example, if you have a 2-qubit system, I will skip this algebra. I'll just show you. The equilibrium density matrix has this population numbers: 2, 1, 1, 0, plus 1 million, plus 1 million, plus 1 million, plus 1 million. Okay, I take away the 1 million this side, or it's 10 to the power 5 here, or 10 to the power 6, doesn't matter. Okay, so actually population of this is 10 to the power 5 plus 2. The population of this is 10 to the power 5 plus 1. 10 to the power 5, 10 to the power 5 plus 1. I remove 10 to the power 5, and you can see later on I will show you that nothing happens to the unit matrix, it doesn't transform. So it doesn't make any difference. Now, this is the equilibrium population distribution. Okay, thermal equilibrium population distribution. If we can convert this into, for example, something like put all these population into one level, then we have a pseudo-pure state. We have a pure state as far as this picture is concerned, but it is riding, there is a million population which is multiplying the unit matrix here. And so it's called a pseudo-pure state. There are several methods for preparation of pseudo-pure states. The first one was given by, again, David Corey at MIT, especially averaging technique, and this is the most commonly used technique. There is one logical labeling technique was given by Gershenfeld in 1927, and we were first to experimentally show this technique. Temporal averaging was by Klein, and Klein I will introduce to you when we come to factorization. A pair of pseudo-pure states, especially, and these are more technical terms, and I will leave it for you. Those really interested can read it. Special averaging technique is this, that we go from the equilibrium system, where the equilibrium system I1z plus I2z, and apply a series of pulses and J evolutions. Okay, and I come to a state which is equal to I1z plus I2z plus 2I1z I2z, and if you look at this has this population distribution. The gradient pulses kill XY magnetization at this point and at this point, and they make it a non-unitary operation. So when you want to go from the equilibrium system to pseudo-pure state, you have to do some non-unitary operations. The non-unitary operations are these gradient pulses which kill the X and Y magnetization at this point, and they kill XY magnetization at this point. If you have to go through the whole algebra, then you will yourself see whether you can come to this or not. Okay. For example, for I1z is this much, I2z is this much, and this is 3 minus 1 minus 1 minus 1. I add 1 to it, it is 0, 0, 0, 4. Okay, that's a pseudo-pure state. Logical labeling technique was Gershenfeld in science in 97, long back over. So basically, this is the 3-spin energy level diagram 4, 3, 3, 3, 2, 2, 2, 1. In which one spin flips, and this two spins flip, and all the three spin flip. Now you can divide them into two subsets. One subset in which the first qubit is in state 0, and one subset in which the first qubit is in state 1. Okay, so these are two subsystems, and then you interchange the population of this by a pi pulse, which is resonating on that frequency, single transition pi pulse. And single transition pi pulse, you get to a population distribution which is 4, 2, 2, 2 and 3, 3, 3, 3, 1. So it's a subsystem pseudo-pure state. Okay, and this has been done by my former student Kavita, who is now a professor at IISc Mohali, uh, and Professor Arvind, who is a very famous theoretician, works in quantum mechanics and quantum system. He was a student, Professor Mukunda here. Both are graduates of IIT Kanpur. And but this is just for demonstration. We don't use it very much. This was introduced by Knill. Knill actually did a factorization of 15 in 1998 or 99, and it made CNN news. He factorized 15 into 5 and 3 using quantum factorization, and it made a CNN news. So what he did was very simple temporal averaging. So he said, okay, I have this population distribution, the equilibrium. I interchange the population of these two in one experiment, and another experiment interchange the population of these two, and add these three experiments. The adding is a non-unitary operation. Okay, and then you come up with a population distribution which is 2 to 2, 6. And so this is a pseudo-pure state. Very clever, very nicely done, but not much used. The most useful technique is this one, spatial averaging technique. Now let me show you some gates. Okay, I mean this so far was an introduction. I'm preparing you for showing how to form gates, quantum gates by NMR. There are two methods, coupling evolution and transition selective pulses. Transition selective pulses actually is our specialization. However, there is a problem with this experiment because you cannot put in a quantum circuit. This you can put in a quantum circuit. So finally, you will have to use this. But just for learning, you can use this. So, for example, I want to do a control NOT operation. Control NOT operation is control on the first qubit and result on the second qubit. It's just a pi pulse on this transition. Okay, pi pulse on this transition. Very easy to do, very simple. Okay, but if you want to use J evolution, you have to apply qubit selective pulses, qubit selective pulses and J evolution, and you go from I1Z plus I2Z to I1Z plus 2 I1Z I2Z, and that is a control NOT operation. A NOT 1 operation is very easy, a pi pulse on spin 1, but then by using transition selective pulses, I apply pi pulse on this transition and this. Basically, this is a spin 1 flip. First spin is flipped. Okay, and so that's a NOT 1. Swap gate is very interesting. It has so many. These are pi pulses. These are pi by 2 pulses. Okay, thick and thin, and you have to do several pulses for swap operation. But here the swap operation very using transition selective pulses. It is very straightforward. You apply pi pulse here, followed by pi pulse here. They are non-commuting, and then we interchange the population of these two levels. And control NOT gate called the Toffoli gate is hard to do here. It's very easy. It's just pi pulse on one transition. Control NOT. Okay, so it works quite well. Now let me show you some logic gates by 1D NMR. This is a NOT 1. I just flip the first spin by pi pulse, and it's a NOT gate on the first spin. I do a control NOT operation, and this spectrum looks like this, and similarly I can do control NOT on first spin, and this is the molecule. So this was somewhat straightforward. swap gate. It has an interesting story. Uh, Kavita was working on this, and she found out that if you apply a pipe pulse here, a pipe pulse here, a pipe pulse here, and a pipe pulse here, three pipe pulses. These are non-commuting. They are equivalent to applying this pipe pulse on the zero quantum subspace. Actually, what she had done was apply a pipe pulse here. Okay, so interchange P3 and P1. Then you interchange P3 to P2, and then you interchange P2 to P1. Then you end up with P3, P2, P1, P4. Nothing happens to these two. So now you can see yourself that's a swap between 0, 1 and 1, 0. And it's equivalent to applying a pipe pulse on a zero quantum subspace. And she was doing this experiment and applying alpha degree pulse here. Then she was able to play in the zero quantum subspace, put any angle pulse. But she found that pi pulse gives you a swap gate. No, she didn't find that. She did the experiment, and this experiment was published by us. And it turned out that it exactly on the same molecule. A year earlier, David Corey had done an experiment and showed that it's a swap gate. And then we realized what we had done was a swap gate. Okay. And this is an experiment in which Toffoli gate basically invert one transition. Control, not this one. Oh, sorry. Okay, I just first, we of course, this was all doing one-dimensional NMR experiments. We also, Richard Ernst mentioned in a paper in 1998 that for doing 2D experiments, he had created these names: creation of initial state, labeling of the initial state, not computation but mixing. He called it mixing, preparation, evolution, mixing, and detection was the names given by Richard Ernst. And then he gave published paper in which he said you can call it creation of initial state, labeling of the state, computation, and reading the output state. And this is very nice. Okay, what you do is to read the states of one of the spins and perform operations on these, and again read back this. And this is what happens with two-dimensional gates, where the input is here and the output is here. So you do a no operation gate, then you see nothing changes. You see a not one gate, so first spin in not, so you see it goes to 0, 1, 1, 0, 0, and this is a not gate. The most interesting is the swap gate. In the swap gate, where we could not distinguish in a homonuclear spin, if we had done a pi pulse between these two, it has very clearly shown up in this map, and so on. Those of you who are curious can go back home. You will get these. This will be anyway put on. You will have access to these slides and check whether these swap plus XOR is correct or not. And so far, nobody has informed me that there is an error here. Okay, 3-qubit system, 2-qubit gates. One qubit is reading qubit, so we lose that 1 qubit. So, but it's a 4-qubit system with 3-qubit gates. All right, up till now we are just forming gates. We have not used coherent superposition. Okay, which is the real power of quantum computer. There are 2 experiments which were written in the beginning, DJ, as I told you, and over such algorithm. I'll show you an example of DJ. Oh, this is a lot of algebra here, but I'm sure you people are smart enough to figure out what's going on. The constant functions are these 2 operations, UF, and nothing happens. F1, F2, and the balance functions interchange this. And the cleave version is given here, and so you have the UF is coming out from this. It's a unit operation, not 2, control not 1, 2, control not 1, 2 bar. Here is the DJ algorithm. 1 qubit DJ has 2 constant functions. So you apply, start from equilibrium, apply a 90-degree pulse, and then apply a UF. The UF that I had mentioned in this slide. These UFs. Okay. And so you get 2 balance functions and 2 constant functions. 2 qubit DJ is the two balance functions and 2 constant functions and 6 balance functions. It's a 2 qubit DJ. Grover search algorithm. That's very interesting. It says if you create a pure state and then apply a equal current superposition, so you get something like this. Then you have an oracle, which is you can't see the oracle. Somebody else, my friend comes and puts the search state, he inverts the search state. I don't know which state he has inverted, but he knows. I mean, basically, when you're searching something, you should know what you're searching. So he says, I'm searching this state. Okay. So he inverts this state, and then you apply a inversion about the average and repeat these two operations root n times, and the search state comes out with high probability, and that's the Grover search algorithm. This is a 1D version Grover search algorithm by using 1D NMR. There is a lot of explanation here. I will skip this and just show you a 2D version. Grover search algorithm using 2D NMR. And here you don't have to see all this, what is written here right now. Just look at the result. And so here is the input state, here is the output state. In the search state, here is 0, 0. Input state is always 0, 0. Okay. And search state is 0, 0, 0, 1, 1, 0, and 1, 1. So this is a clear demonstration of Grover search algorithm using 3-spin system in which one qubit is a labeling. All right. There are there are many experiments done by very large number of people, um, especially from Corey's group and in MIT, and those with tick mark we have also done in our lab. And the preparations of quantum knowledge gates. What we have not yet done is source algorithm. Okay. Bell state discrimination, I will show you that. And creation of EPR and GSZ state is straightforward. Quantum games, we have implemented some quantum games. Entanglement transfer and a no hiding theorem. I will show that also. Okay, what is the number of qubits? We have got maximum 8 qubits in Laflamme with David Corey and my former student Mahesh, who is a professor at IISc Pune. He was a postdoc with David Corey, and they, in 2006 they got 12 qubits. Okay, our own contributions are distributed into 8 PhD theses and nearly 40 publications. A couple of them, a few is not wrong, a couple of them are briefly highlighted in the following. So, non-destructive discrimination of Bell states. Okay, Bell states are maximally entangled 2-qubit states. There are 4 Bell states. This is the symbol, and the state is this 0, 0 plus 1, 1. Okay, this is the entangled 2-qubit state. You cannot write this as product of 1 qubit states of spin 1 and 2 qubits. So therefore, they are maximally entangled 2-qubit states. Okay, and there's a 0, 0 minus 1, 1, 0, 1 plus 1, 0. These are 4 Bell states, and they play a very important role in teleportation protocol and whatnot. There was a paper published by Protocol for Non-Destructive Discrimination of Bell State by Professor Panigrahi, who was used to be at IIT Kanpur earlier. Now he's in professor in IISc Calcutta. Okay, they published this paper later on, but a theoretical paper requires 2 Ancilla qubits and 1 measurement on each Ancilla. My former student Jharna Rani, who didn't live long enough to see this paper, implemented the above protocol using one insula and two measurements. So the Pani-Gray circuit required 4 qubits and prepared the Bell states only once, and through local operations distinguish which Bell state is this. Okay, we had only 3 qubits, so we performed 2 separate measurements, one this one and one this one. Okay, and for phase measurement and parity measurement, we managed with 3 qubits. We have to prepare the Bell states again. All right. So these are again first measurement will give you this. If you have 0 0 1 0, then you get these are the signatures of these Bell states. The experiment was performed on this molecule that I showed you earlier, this dibromofluoromethane, and carbon 13 labeled, and it has interesting spectra that I showed you very much in the beginning. And then you produce a pseudo-pure state. In this case, we did using only nearest neighbor coupling, and these are the various pulses one has to apply. And this is the tomography of the 010 PPS. What it shows is that only excess population in one state. It's a pseudo-pure state. This is a beautiful demonstration of a pseudo-pure state in a 3-qubit system like this. All right, this single diagonal element. The pulse sequence for discrimination of Bell states has 4 parts: preparation of pseudo-pure states, which is earlier done, preparation of Bell states, encoding phase and parity information. For parity measurement, Hadamard gates are removed and C0 gates are reversed. So this is phase measurement circuit. And this is, of course, another representation of a pseudo-pure state, that this shows that we have excess population in only 0 0 0. All others are equal. And if you take the spectrum, then I should see one line for each of these 3, carbon 13, proton, and fluorine. And so this is also a very good indicator that it is has excess population in only level 0 0 0. Okay, of course, if you do this, it's more pictorial. Tomography is more pictorial, but to do the tomography, we have to do a large number of experiments, read the whole density matrix. But here we just need single experiment at each spin, and so it's easier to read it. That is the pseudo-pure state. Basically, this is the equilibrium spectrum, and this spectrum is a indicator that we have only excess population only in this state. All others are equal. So because all these transitions are missing in this spectrum. So these are the created Bell states, tomography of created Bell state, psi plus, phi minus, psi plus, and psi minus. This is showing that we can create the Bell state. The population spectra of C13 after discrimination shows first measurement, second measurement, that we can see which Bell state it is, and it's a non-restricted. Okay, this work was published way back in 2010. Then there was another interesting experiment we did. That there was a Professor Pati, who is a professor in HRI, HRI Harishchandra Research Institute in Allahabad. And they have a very good group, 4 faculty members and 20 students and postdocs in a small institute. And Professor Pati moved from, he was in IOP Bhubaneswar and moved to HRI about 10 years ago. So what he showed in this paper, this is Brownstein and Pati paper in Physical Review Letters in 2007, any physical process that bleaches out the original information is called hiding. If you start with a pure state, this bleaching process will yield a mixed state, and hence the bleaching process is non-unitary. However, in an enlarged Hilbert space, this process can be represented as unitary. No hiding theorem demonstrates that initial pure state after bleaching process resides in ancilla qubits, from which under local unitary operation is completely recoverable. Okay. So this was the circuit given by them. They create a Bell state, one of the Bell states, and then perform these two Hadamard gates and a U operation, which is randomization operator, and then through local operations, this is control knot, Hadamard control knot. You see, they have mathematically shown that the psi will appear here. Okay, in this paper, they have mathematically shown the psi will appear here. My students did the experiment by NMR, and the conversion of geometrics into NMR pulse sequence has been achieved here by a novel algorithmic technique developed in our lab by Ashok Ajoy, and we published that in 2012. A little tidbit: Ashok Ajoy did his masters from BITS, Pilani, Goa. Did his PhD from MIT, and they did postdoc at UC Berkeley, and is now with very well-known Professor Alex Pines of NMR group. And now he just last year became assistant professor in Berkeley. That's a fantastic. He was really very good, and he wrote out this mathematics, and we use this. The equivalent pulse sequence for U matrix is obtained as this, and here's the experiment details, and the results are here. Jharna Rani did 525 experiments, been performed by varying theta and phi in steps of 15 degrees. Each point in this surface is a pseudo-pure state. Okay, and so first you create a pseudo-pure state, all right, and then run the experiment and create a phi. Okay, and then in the output state, you see this is completely recoverable in the ancilla qubit. The state psi is completely transformed from first qubit to the. Oops, sorry, I don't know what I did. Ankur, how do I go back? Padma, Ankur bulana. What do I do?
So are you trying to go back one side?
Yes.
The left arrow key usually works.
Eh?
The left arrow key usually works.
Arrow key.
On the keyboard, the left arrow key usually works to move it back one slide. It's not working.
Wait. Backspace doesn't work. Tab. Shift. Oh, 1 second. Let me see. Ankur, come. Something I did it went off. No. In the screen. I pushed one button wrongly.
No, you're still there. You're still presenting.
Okay, what did you do? No, what did you hear?
You clicked on this or something like that, and that came up, but you still have this.
Okay. All right. So this was a beautiful experiment, and it was published in Physical Review Letters. My only second PRL in my life. Okay. Now, this is some kind of an end, but I have something more to come. And if I have run out of time, no, I have not run out of time. I will still have 5 minutes. All right. I'll show you something very interesting that you will all appreciate. Okay. IBM recently, I'm sure many of you know this, If you don't know it, this is good. Then I'll tell you now. IBM in 2016 released a 5-qubit and a 10-qubit superconducting based quantum computer called Quantum Experience and placed it on the cloud for use of one and all, free of cost. Okay, so my 2017 summer students, these three, Ayan Majumdar, Santanu Mohapatra, Purvika Bala, uh, they did 3 experiments using this quantum computer. Non-destructive description of Bell state that we had done by regular NMR, non-destructive arbitrary set of orthogonal quantum states. I didn't talk about it. This student Manu discovered it himself. And then experimental test of quantum no hiding theorem that I have just now shown you. Okay, let me show you what happens now. So this is the hardware of the IBM quantum computer. It is in Bell Labs. It's very cold, in dipped in liquid helium, and it has superconducting qubits, and there are connectors and whatnot, and these are various connectors. In order to minimize energy loss, the coaxial lines that direct signals between first and second amplifying stages are made of superconductors. Okay. Then you build superconducting qubits, and then you have to build coupling between them, capacitor coupling. And they had built some couplings in the beginning, and they added more couplings afterwards. So I think these 2 couplings were added afterwards. Somebody had done the experiment, non-distributive discrimination, using older version, but by the time we started, they added these 2 couplings between Q3 and Q4 and Q1 and Q0. So, and the way it works, that you can pull down each, these are the X, Y and Z gates, Hadamard gate, uh, identity, unit, and uh, various gates are here already built in. So you pull them here, from here to here, and oops, sorry, yeah, and then make a circuit. All right, I'll show you that coming up next. Okay, so here is the circuit for Bell state. So you start from a pure state, they are all in pure state. Then you build a Hadamard gate and a control NOT gate and take a measurement. Okay, measurement on the first qubit and the second qubit using Ans's law. So this is the probability finding system in state 1, 1, and the probability finding system in state 0, 0. And the number of shots were 100. If you increase the number of shots, the fidelity improves. Okay. This experiment was verified already by Anirvan Pathak's group in JPIIT in Noida. Okay. And because we had done an NMR experiment on the non-distributed distribution, he contacted me trying to find out what fidelity I got by NMR. By NMR, I got a fidelity of 4%. Okay. And so then I learned about this IBM quantum computer from Professor Anirvan Pathak. And I used the new version of the device and fewer gates and got high fidelity. Okay. So the whole purpose of showing this is to excite you. Okay. This experiment for no hiding theorem was also repeated by using this, and the U matrix here is very complicated, but the students were able to work it out. The U matrix here, the students were able to work out what exactly has to be done, and they found the quantum state computational basis probability of a third qubit state half. And then extraction to Bell state. Okay, and so the non-distributed discrimination of Bell states. No, sorry. No hiding theorem. Proof of the no hiding theorem is contained in this. Okay. So I just want to tell you that Every one of you can go to Google, go to this site and use this quantum computer. And there are stepwise instructions how to use it, and you can repeat several experiments yourself. And so just get excited, that's all, and you can do it yourself. You don't need NMR, you don't need any hardware. The hardware is in Bell Labs, but they are given access to you through the cloud, and everybody can use the free. Okay, and the 10 qubit system that they have, there you have to not pay, but you have to identify yourself and get a okay from your professor, and then professor has to also certify that is a bona fide student. For the reason is they don't want the people who are making money to use this free. Okay, then they charge the others, they charge money. Thanks to IBM for developing such a wonderful experimental setup and making it available to one and all. And there is a great excitement in quantum computing field. The pessimism of yesteryears, in which people were wondering that will a quantum computer be built in our lifetime? That's, for example, my lifetime has been replaced by optimism that a quantum computer will be built in next few years. And few is not defined. Okay, uh, which will beat the fastest classical computer. Uh, Summary, NMR is continuing to provide a test bed for many quantum phenomena and quantum algorithms. And I have acknowledgement slide, many of my former students, and especially this lady who was murdered by a deranged man. uh, and she left enough work for writing a thesis in 5 years. These are my latest students who have moved out also. I have benefited tremendously from discussing with Professor Apurva Patel, who is a theoretician in our institute, in our high energy physics department. These two are my colleagues in NMR Center, and I have benefited tremendously by talking to Professor Malcolm Levitt from UK, Professor Panigrahi, I have collaborated, Arun Pati, I have collaborated, Ajit Sen, Arjun Sen, I have collaborated, and I couldn't show their work, the beautiful work that has been done by Koteshwar Rao and Ashoka Joy, funding DST, DAE, etc. And I thank you very much.
So I have a question.
Yes,
If we look at the problems quantum computing faces currently, decoherence is a pretty big one, which is
yes,
basically the tendency of a quantum computer to decay from the quantum state to
yes, sir.
incoherent states due to environmental interaction. So is anything
Yes.
being done to counter this? Like, can we increase the decoherence time somehow?
Well, um, decoherence is a great menace for quantum computer. Okay,